Welcome to today's lecture. During our discussion so far, we have now have an understanding about the various types of inclusions as far as their compositional types are concerned and their appearance at room temperature in combination of different phases, liquid, vapor and solid, in different types of crustal environments coming from an ore body or from a rock. And we now know how to look at them, how to see them, identify them, and then do a background study of petrography, fluid inclusion petrography, and then go on to carry out the microthermometric experiments on the different types of inclusions, and then present their data and interpret the data in relation to the variables, the compositional variables, the intensive variables like pressure and temperature, and then integrate them into other information and address the issue, whether it is the issue of genesis of an ore body or addressing the issue of the characterization of the fluid in causing the metamorphism and so on. So, in this lecture and the following subsequent lectures, we are going to discuss on the application of fluid inclusion studies to understand ore deposits. And to begin with, we must keep in mind that those deposits which broadly come under the category of hydrothermal deposits means the deposits which owe their origin to the activity of hot aqueous fluid, ore fluid, are the ones which are amenable to such fluid inclusion studies, and basic objectives in this methodology lies in identifying the nature of the ore fluid, their probable sources from which they have been derived, and then the way that they evolved in space and time. Before we go into this, it would be worth pointing out that the fluid inclusion studies, majority of the volume of the fluid inclusion studies carried out over the past half a century or so, majority of them are devoted to study of ore deposits and hydrothermal ore deposits. So, the literature on them is dauntingly vast, and it is not possible practically to give a very detailed idea or going into the to an exhaustible review of the application of fluid inclusion studies to ore deposits. And we also know that essentially the hydrothermal deposits that we know of, the hydrothermal deposits that generally we discuss, we always discuss in terms of the possible sources of such hydrothermal fluids, and we know that the hydrothermal fluid, the temperature range could be anything from starting from 50 degrees Celsius to greater than 500, even sometimes even greater than 600 degrees Celsius, as some of the cases we will be considering. And the another so this is the kind of the temperature ranges that we see in the hydrothermal deposits, and their composition, gross chemistry, the way that we have expressed them as salinity in wet percent NaCl equivalent, can be very close to 0, almost sometimes pure water, to values sometimes which will be almost like 70 wet percent or near about that. And we also know that these hydrothermal fluids can have a very diverse source, and the sources of them dominantly they could be magmatic, metamorphic, cornet and meteoric. The meteoric also sometimes even we can include seawater, which is a modified meteoric water. We know it contains about 3.5 weight% in terms of salinity, and we know that all these are the dominant types, and some other type like the juvenile water, its involvement in wood deposit formation is not that very well known. And the magmatic deposit, magmatic fluid, metamorphic fluid, cornet fluid, meteoric fluid, they are all having their own identity in terms of their temperature and salinity characteristics. So, the basic idea is that whenever we are attempting to study the origin and evolution of a hydrothermal ore deposit through systematic fluid inclusion studies, selecting the fluid inclusions, the appropriate ones, classifying them into different types, and then taking their microthermometric data. So, we would like to essentially unravel the fluid origin, or what we say the ancestry of the fluid, and not only that, with the help of a fluid evolution diagram that we saw before on a salinity and temperature homogenization plot, we generally see that there could be many possible trends, like a mixing trend, like a boiling trend, could be different types of mixing trends which can be decipherable from the paired salinity and temperature of homogenization data, and then we can decipher about the fluid source, the fluid the path of the fluid evolution. So, now on that backdrop, I would just like to start with the diagram. This diagram is a composite diagram on the temperature versus salinity in weight% NaCl equivalent as shown here, and delineating the fields of some important hydrothermal ore deposits, porphyry copper deposits, the skarn deposits, which are the essentially the tin tungsten deposits. Porphyry copper are the copper, molybdenum and gold. There are some pegmatite related tin tungsten deposits. The epithermal deposits which occur in the top brittle deformation zone of the Earth's crust, and the lode type gold deposits are known as the orogeny gold deposits, the Mississippi Valley type deposit. What we can see here, that these kind of a broad framework can be possibly proposed, collating or synthesizing information from innumerable such ore deposits of occurring in different parts, different continents, and then summarizing the data and trying to make a generalization, although exceptions will always be there from such generalities. And these are the different types of different areas like the porphyry deposits, skarn, the tin tungsten deposits, epithermal deposit, iris deposit, lode type gold deposit, Kuroko deposit and Mississippi Valley type deposit. And some of the as I told you that such kind of discussion can be it's very difficult to make an exhaustive summary or exhaustive review, as we know that there are many other such important deposits also which are missing from this this synthesis. There are the important very rich the Carlin type gold deposits which occur in the western United States, in the states of Nevada mainly, and the unconformity related uranium deposits like the Athabasca basin and the MacArthur basin in Canada, or Alligator River basin in Australia, and the iron oxide copper gold deposits of the type of the famous Olympic Dam deposit, where there are rich mineralization of copper, gold and uranium in a single locality, and in an area in the Gawler Craton in South Australia, and different pegmatites rare element bearing pegmatites, tin tungsten bearing pegmatites, which also do have some very characteristic fluid in terms very in their characteristics of fluid is very important, and they are also an important class of the ores which contribute different types of metals and minerals to the industry. So essentially these kind of diagrams will always be pertaining to the characteristics of the aqueous fluid, because we should also keep it in mind that we are plotting the homogenization temperature versus salinity. So and at the most these kind of diagrams can have the data from the aqueous biphase inclusions, from where we determine the salinity from the depression in freezing point of ice and the temperature of homogenization. These data also do include the halide bearing polyphase inclusions, where we also determine the salinity. As you can see, the halide saturation curve is also plotted here compared to the diagram which we presented, the composite fluid evolution diagram. Here is the critical curve. So it would be interesting to see when we are introducing this particular course for beginners, and to appreciate the application of fluid inclusions and to pick this topic up for their further study, pursue this particular methodology and technique for their research. It would be always necessary to look into some of the case studies or a detailed analysis as to how a particular model on the origin and evolution of the ore fluid could be formulated, could be sort of synthesized from fluid inclusion data, right from the point that we identify inclusions and classify them, take their thermometric data and present them on conventional plots. So this whole process we have to demonstrate through some selected case studies, and while doing so it is also important to note that the model on origin and evolution of ore fluid in any deposit is definitely not solely based on the fluid inclusion data, and right at this when this was so, when there were no much of sophisticated instrumentation available, and maybe 3-4 decades back when the such fluid evolution model could be presented solely based on fluid inclusion data. But it is also important to substantiate or correlate or make the fluid inclusion data corroborated from other sources such as the stable isotopes, which also isotopes of oxygen and hydrogen, sometimes even carbon and sulfur. These are also analyzed from as and when they are possible, either through the alteration minerals or from the fluids which is extracted from the fluid inclusions, so that the model on the fluid origin, such as a fluid mixing model or a boiling kind of model or cooling kind of model, it is more so it's for the mixing kind of model, which need to be corroborated or is better corroborated, substantiated through data such as other data such as stable isotopes. So with this backdrop, we would like to just make a brief look in some of the ways that the data have been presented. So this diagram has been taken from Mukherjee 2000, a book of Orogenesis, a holistic approach, where we try to make a diagram for general understanding as to what are the different possible scenarios that have so far been presented in the context of some important deposit types. The ones with this kind of hatching, which is labeled as NEG, is the New England batholith in Australia, in the South England batholith, where there is occurrence of tin tungsten mineralization. So we could see that this deposit, the fluid, has been interpreted to have evolved in such a complex manner, starting with a very high temperature, very highly saline fluid, boiling fluid, which is evolving down to intermediate temperature and salinity values still in the two phase field, and then with gradual warming of the magmatic phase with incursion of low saline, low temperature emitting water, it is actually giving rise to a mineralizing system which starts with barren quartz topaz kind of rock, and then with veins of cassiterite and quartz, and then finally giving rise to the sulfides in the veins in the late alteration assemblages. This is an interesting scenario, the Malanskhand scenario, where this is the fluid there is mixing of two fluids which is interpreted, which we will be discussing in the little bit of greater details. This is the kind of a mixing trend which has been interpreted for a vein type deposit, and what is marked here as CR1 is the epithermal Crete deposit from Colorado, and the kind of salinity temperature variation that we get again with a mixing trend. And the one which is shown here is MVT1, which is the Mississippi Valley type deposit, and 1 and 2. There also we find that there are mixing trends which are established between fluids of high salinity to moderately low or low salinity kind of fluid, all both being falling in the low temperature regime. And this box joining the Dachang polymetallic deposit, here also a mixing trend is established between the fluid with very high temperature salinity to very low temperature and low salinity kind of fluid. So these are these cases whose references will also be detailed in the handouts. It is always good to look at those work and look at the fluid inclusion characteristics, how this kind of model or how this kind of synthesis has been made to understand the fluid evolution. Like the one which I was showing here, this is the scenario taken from caledronite sulfide deposit, in the sulfide deposits in the caledronites in Sweden. There are which the authors represent in a very decorated manner. If the salinity and temperature recorded from different like for example the black dots are representing from calcite, the triangle from sphalerite, and the square from fluorite. So these inclusions, fluid inclusions, their salinity temperature characteristics are falling in this kind of band, which the author interpreted in terms of mixing of two fluids as shown by the fluids in two beakers, the identical temperature, and the one component having salinity as high as almost 36 weight percent NaCl to temperature of 14 weight percent NaCl, and these being interpreted as two different types of fluids. Now when we get such kind of mixing trends, it definitely is a subject of debate or discussion as to what origin or what ancestry we would assign to this particular fluid components when there is a mixing. Normally any fluid which is a low temperature but a salinity, high salinity, sometimes varying to 25-30 weight percent NaCl, we generally ascribe them to a cornet source, because those are the fluids which are mobilized from the sedimentary strata and are never subjected to very high thermal perturbations, and they generally migrate long distances and they carry the metals and deposit with encountering some different physicochemical environment. So the general idea, whenever we see a very high temperature and very high salinity fluid with the salinity going to 70% or more, there the general idea is that this fluid must be a magmatic fluid, because these magmatic fluid generally result from exsolution of the volatiles from a crystallizing granitic magma, and during the situations corresponding to a first boiling or a second boiling kind of condition in a granitic magma, the fluid which gets partitioned into the fluids which get separated from the crystallizing melt, the most of the volatiles and the light elements and most of the species are getting transformed in addition to the base metals as well. get transported into the volatile phase, and that becomes very high saline. And then generally a fluid which will be very low in its salinity and temperature is generally ascribed to a meteoric source, because that meteoric fluid has retaining its signature, chemical signature, has only been channelized through the fracture network in the rock, and that is how it potentially can mix with many other fluid sources like a connate fluid or a magmatic fluid, and give rise to mineralization. So, we will just see one of the, this is of course from old literature, this is from Eddington 1983. It is from the mole granite, where a classic tin tungsten pegmatite base metal sulphide mineralization system in the New England batholith in the Eastern Australia. So, the component of the mineralization is an early magmatic quartz topaz rock, which is not which is the stage at which there was no much of deposition of the ore minerals. So, it is essentially a quartz topaz rock where the salinity of the fluid is from 50 to 65 weight percent NaCl, and temperature is high, almost more than 620 degrees Celsius. These are all determined from the homogenization data, but these temperatures are also not pressure corrected as suggested by the authors. Then it gives rise to a complex pegmatite, biotite, beryl, topaz, fluorite and quartz characteristics varying from high temperature to high salinity again, and to moderate evolving down to temperature low as 300 degrees Celsius. Then it gives rise to a disseminated wolframite mineralization, quartz, sericite, topaz, and then the main cassiterite quartz vein in the unaltered granite, where the temperature is decreased substantially and also the salinity, and then disseminated catarrhite, and then the base metal sulphide quartz veins as shown in the diagram with argillic alteration in the granite, and cross cutting potash felds where there is adularia and quartz veins in the early hydrothermal ore, which is the sulphide. So, this is just for our own visualization, that whenever we say that the fluid was a very high salinity, means definitely this fluid must have been manifested in form of polyphase or halite or even more than one daughter crystal bearing inclusions as shown here. This is a diagram for the multiple daughter phase bearing aqueous inclusions in topaz from the quartz topaz rock, representing very high temperature and very high salinity. These are the polyphase aqueous inclusions in quartz from the complex pegmatite. The polyphase aqueous inclusion in beryl again with complex pegmatite, and these are the polyphase inclusions from the quartz cassiterite veins till the stage that the fluid is maintaining its high salinity condition. The composite diagram which just I showed, it is taken from here only. So, this represents the temperature of the order of 600 or more. This is the quartz topaz rock from which inclusions were studied in topaz. This is the complex pegmatite where the inclusions are studied from also beryl as well as quartz. Most of the times inclusions could be studied in more than one such minerals of the constituent ore, and interpretations can be made. And so, now the interesting thing to observe here is this area which is marked by hatching is essentially the situation in which there was a the fluid was in its in the heterogeneous condition, means vapor and liquid coexisting conditions, or in other words corresponding to a boiling situation. So, that means the fluid was in fact having a high salinity liquid plus a low saline vapor, and as interpreted by the author. So, this existence of the vapor in the two phase condition of the fluid did not allow the extraneous fluid or the meteoric fluid to get into the system and to dilute. Only when the temperature substantially reduced and the vapor condensed, then only the condition was more conducive for incursion of the meteoric water, low salinity meteoric water to come and mix with the system. And so, these are the dashed line are the density contours. So, the two stage, so the authors now from the inclusion data where the homogenization was mostly obtained through the dissolution of the daughter crystals, and whatever was available to calculate the salinity and density. And it was a two stage evolution. Stage 1, it was a two phase fluid, and the stage 2, after the condensation of the vapor, it got converted into only one stage. So, that means in the lower temperature region, the inclusions were only like has been shown here, they were all the liquid rich inclusions, sometimes containing the daughter crystals with high salinity, as well as towards the waning phase to the base metal stage, the fluid changed its condition from to a low temperature and low salinity character. Now, the interesting situation here is that in this particular deposit occurrence, there is no report of occurrence of any carbon dioxide rich inclusions. It has always been a aqueous fluid. Although there are many other such situations where the transportation and deposition. So, when we are talking about, in this case, it is the deposition of cassiterite tin, which gets transported in the form of in a condition where it is in SN2 plus condition, where the condition is supposed to be reducing, and then it has to encounter a condition. So, those kind of reducing conditions are sometimes ascribed to the presence of carbonic component in the fluid, which is not observed in this particular case of mole granite. So, we are discussing these as, and then coming to another situation where we discuss about another polymetallic mineralization involving a proximal skarn and a distal skarn. The proximal skarn constitutes of copper, lead and zinc mineralization, and the distal skarn is cassiterite sulfide deposit. So, here the authors have interpreted multiple stages of the fluid activity in this proximal as well as the distal skarn, and even though it is not I mean time or the scope, within the scope of this discussion, it does not allow us to go into the details of the mineral paragenesis that was deduced by the authors, but such kind of the proximal and the distal skarns and the fluid inclusion studies in the different minerals has to be very much backed up with paragenetic sequence, reduction of the paragenetic sequence, so that we know exactly which fluid we are sampling from which stage of the evolution, which stage of the evolution of the fluid. And in this, where in the stage A and B proximal ores have polyphase aqueous inclusions, the stage B has aqueous carbonic inclusions in the quartz, cassiterite and fluorite and carbonate in this Dachang polymetallic deposit in People's Republic of China. This has been taken from Kwok and Marendog in 1993. So, the aqueous biphase is high saline in proximal ores and low saline and distal ores with carbon dioxide detected in the vapor phase. These are both liquid and vapor rich, and this diagram is again a composite diagram, which we will see the situation is somewhat comparable to the one which we discussed in case of the mole granite, but here it is a typical skarn deposit, and this proximal skarn and the distal skarn, as you could clearly see here also, the proximal skarn, which is essentially developing a vesuviohanite mineralogy, typical skarn mineralogy, and its fluid inclusion characteristics are with very high temperature, more than 600 degrees Celsius, and high saline, and the fluid gradually evolves to the distal skarn, the stage 3 of the distal skarn, in which it is a calcic calcalic sort of the fluid becomes more more and more in pH, and it gives rise to deposition of calcite. Sulfides like galena, stibnite are deposited in the distal skarn in the cassiterite sulfide stage, and we could see the situation in which all these the histograms representing the temperature of homogenization of the fluid inclusions. Fluid inclusions, as you could see here, studied from cassiterite and quartz both. So, this also is a situation in which similar involvement of less evolved low saline low temperature fluid with high temperature high saline fluid of magmatic derivation is giving rise to the mineralization. Okay, so we will continue our discussion on the application of fluid inclusion studies to the ore environment, and we will take up other case studies which will also give us some more insight as to how we can judiciously interpret the fluid inclusion microthermometric data, and with our knowledge on the solubility of metals, the chemical control on transport and deposition of the metals will correlate, and we will continue discussing in the next class. Thank you.